So in this video, I'm going to be talking to you about titration curves and the basics of titration curves, along with some calculations that will enable you to construct your own titration curve, specifically related to strong acids and titrated with strong bases. So if you have never learned about titrations and titration calculations, this is probably not the right place for you to start. I would suggest looking at alternate videos, which I can certainly link up in the description. Let's start by reminding you of the basics of titration. So the point of a titration is basically to figure out the concentration of a substance when you don't know its concentration. And so how you do that is you typically have this piece of equipment called a burette. And the burette has this stopcock, and the stopcock can be turned to allow a small volumes of material to be added to the Erlenmeyer flask. So let's talk about specific terminology related to acid-base titrations and titrations in general. So typically you'll have an Erlenmeyer flask containing the substance whose concentration you don't know and you're trying to figure out. That substance can be either called the analyte, okay, the substance being analyzed, or sometimes it's called the titrand, the substance being titrated. Okay, so then in the burette you'll have a solution whose concentration is known and is known very accurately and precisely. That substance is called the titrant. Okay, so the titrant is placed in the burette, and you're slowly going to add it to your analyte or your titrand. And the hope is that you have added an acid-base indicator so that at a certain point in the titration you will see a color change, and that color change indicates an end point to the titration. The titration is over at that point. So that's your basic setup. So there's some other terminology that I want to talk about, so let's go there next. And so the standard solution is the name we give to a solution whose concentration we have deliberately created with a lot of accuracy and precision. We want to make sure that we use a standard solution as our titrant, because remember, we're relying on its accuracy and precision in order to, do some stoichiometry, some calculations to allow us to uncover the concentration of our analyte, right? So we need to know that. We need to know the concentration of our titrant very, very precisely, so we'll use typically a standard solution. One other term I want to talk to you about, and I want to differentiate between it and the endpoint, is the equivalence point. So the equivalence point is a point in a titration where you have neutralized all substances. So if you're doing an acid and base titration, then and you have acid in as your analyte, then enough base has been added so as to neutralize that acid. That is called the equivalence point. Now, ideally, you want your endpoint to signal your equivalence point, but those don't always overlap, right? And if your endpoint is too different than your equivalence point, you may be stuck with some error in your analysis. So that's important to consider. So equivalence point is kind of sometimes called the stoichiometric point, because that's when the theoretical neutralization point is kind of there, and you can look at the math, whereas the endpoint is more of a qualitative piece. It's you're observing when there's a color change. Hopefully, though, the equivalence point and the endpoint are somewhat aligned. Okay, so the main point of our discussion today is to help you understand what a titration curve is and how to construct one, how to perform calculations in order to construct them. Okay, so typically we will have pH in an acid-base titration. We'll have pH as our dependent variable. We want to see how pH changes as a function of changes in the titrant volume added. Okay, so we're going to be adding our titrant slowly, and that's going to cause a change in the pH of our analyte, right? And so over time, it looks to me like we start out with a very low pH, and the pH steadily climbs. So what that's indicating to me is that we probably have here a depiction of a strong acid solution as our analyte that is titrated with some base. And as that base is added, it's going to neutralize the acid and the pH is eventually going to rise. So here we see on the graph this equivalence point. Typically that's sort of like the midpoint in that roughly vertical portion of our graph. And that aligns with the pH at that equivalence point. So that's super helpful for us to know. And so another piece that I want us to understand is that because in this case we are looking at titration curves of strong acids with strong bases, we need to understand what makes an acid a strong acid and what makes a base a strong base, because weak acids and bases behave slightly differently, and their curves are going to, correspond as a function of that difference. They're going to look different. So we need to remember that a strong acid is going to dissociate 100%, and a strong base is going to dissociate 100% or near 100%. So here's a visual depiction of that. If we're looking at a strong acid and we kind of zoomed in on it, we would see that every acid particle has dissociated into its respective ions, whereas a weak acid, you will see, some of the particles have dissociated, some ions are present in solution, but a reasonable proportion of undissociated acid molecules are present in solution, so they're not contributing to the pH. Okay, and so the same holds true for bases. So that has an impact on how we do our calculations, right? And so what that means for us is that the acid concentration will essentially be the same as our hydrogen ion concentration in solution. And the base concentration will be equivalent to the hydroxide ion concentration. So let me, maybe this visual will help you to understand that. If I have a strong acid, and HCl is certainly like a key example of a strong acid, it's going to dissociate 100%. So every single particle of HCl is going to dissociate and liberate hydrogen ions. And so if I start out with a concentration of 1 mole per liter of my initial acid solution, HCl solution, then that I can count on there being, can reasonably make the assumption that the concentration of hydrogen ions in solution is also going to be 1 mole per liter. Bases, same dealio. So I'm starting out with 1 mole per liter solution of sodium hydroxide, and sodium hydroxide is a strong base. Then I can expect that that's going to liberate, then every single particle of NaOH is going to be dissociate into its respective ions, and I can count on the hydroxide ion concentration being the same as that initial sodium hydroxide solution. So those are some key things that I'm assuming when I do calculations and constructing a strong titration curve of a strong acid with a strong base. If I have a weak acid or a weak base or both, then the calculations have to change as a function of the behavior of those weak acids and bases. Okay, and so let's talk about, next we're going to get into an example that will help you perform calculations and construct a titration curve of your own for a strong acid titrated with a strong base. Okay, so in this is a pretty typical example of a task you might be assigned in senior chemistry or even first year university chemistry, which is to construct a titration curve. And so in this case, they are giving us the amount of our analyte and the amount of our titrant. So we are titrating nitric acid, which is a strong acid, with a strong base, sodium hydroxide, and they're giving us the amount of nitric acid and the concentration of our sodium hydroxide. And so in this case, we know the concentration of both, and we want to see the behavior of our analyte as the pH changes when we add our titrant. Okay, so let me kind of create a bit of a visual for you. Okay, so what do we have here? Well, we have our Erlenmeyer flask. So we have our Erlenmeyer flask here, right? That's our Erlenmeyer flask is going to contain our analyte. And our analyte, in this case, they're telling us we have 50 milliliters. So let's just imagine that this is the 50 milliliter line. And that's where our HNO3 is. That's where our acid is. right? And we know its concentration is 0.200 moles per liter. And then so then we have our burette, and we have our burette. Here it is. I'm just going to kind of, fake it a little bit here. People imagine this is our stand, and we've got our burette in here. Here it is with its stopcock. And then we're going to fill that burette with our titrand. And our titrand, in this case, is the sodium hydroxide, right? And we know its concentration is 0.100 moles per liter, right? And so we're going to start adding dropwise. We're going to add our titrand into that analyte, okay, and then see the pH, how the pH changes. Okay, so essentially when we do our calculations, what our goal is to figure out here is to figure out the data points, right? Here, 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 a few data points to get us started so that we can eventually join those data points and create that nice curve. So we're essentially trying to create a table of values, right? So I would start by picking some sort of key values, like probably 0 milliliters, right? And then kind of work my way up, maybe get to, 10 milliliters, and then skip over a bit. And it's just like anything, we're doing a bit of trial and error here to get some key points, and then we can narrow in on where we need more data points once we have kind of a starting place. So, here, so we're going to try to figure out through calculations what the pH associated with each of these sodium hydroxide additions and what changes in pH we're going to observe. And each of these are going to create like a coordinate that we can plot to create that titration curve. So let's get started. I usually like to start with, well, what is the pH of my solution initially? And so I'm going to go to 1 decimal place because I see that my analyte has a volume measured to 1 decimal place. And so I'm going to first start by trying to figure out, well, before I add any of my sodium hydroxide, what is the pH of this solution? So before I start my titration at all, the pH, the only thing contributing to the pH is that nitric acid and the hydrogen ions that get liberated from that strong acid. So now again, remember that there's 100% dissociation here. So if I started out with 100 molecules of my nitric acid, I'm going to liberate 100 ions, hydrogen ions, right? And so the same holds true with my concentrations. If I'm starting out with a 0.200 mole per liter solution of nitric acid, then all of that is going to get dissociated and into solution. So I can safely assume the hydrogen ion concentration in my solution is 0.200 moles per liter. Okay, and so you'll remember from a grade 11 chemistry that we can calculate pH by taking the negative log of our hydrogen ion concentration. And for our purposes, we're going to assume that when we say hydrogen ion concentration, we also mean hydronium ion concentration. Okay, so we'll just keep that in mind. Those are going to be interchangeable for our purposes. So the negative log of 0.200 is going to be 0.69, and I'm going to say I'm going to write that value out to 3 significant digits. Okay, so that's my pH value. So that now I have 1 data point. I know that my initial pH of my analyte before any titrant is added is 0.699 moles per pH of that. Okay, so that wasn't too bad. It's going to get a little bit more bumpy in the next few stages, so just pay close attention while we enter phase 2 of this situation. All right, so now on to phase 2. So I want us to envision that we've started our titration and we've added 10 mils of our titrant, right? So we've opened up that stopcock and we've allowed 10 mils of our titrant to go in, right? And so again, just to create that visual, right, we've got our Erlenmeyer flask and we started out with 50 mils of our HNO3, and then we're going to add in 10 milliliters of our sodium hydroxide, okay? So that's where we are so far. So let's examine what we need to think about in this, right? So we know that acids and bases react in neutralization reactions, right? And so when I add a little bit of the base to the nitric acid, I can see that they're in a 1-to-1 ratio, right? And so any hydrogen ions that get produced are going to get neutralized by the hydroxide ions, right? And so, but not all of them though, just a few, because I've only added 10 milliliters of my base so far. So presumably it's going to be able to neutralize some, but not all of my acid, right? And so those excess hydrogen and hydroxide ions are going to combine to form water. And we're going to come back to that when we get to, I think, phase 4 of our operation. So recognize that, you know, only some of my sodium hydroxide is neutralized, or sorry, only some of my acid is neutralized, but that the surplus hydrogen ions are going to be contributing to the pH. And in this case, there's going to be a surplus of acid particles. And so the acid, I'm going to expect that my pH is still going to be in the acidic range, although it's going to be a little bit less acidic than it was before I added the sodium hydroxide. So that's really important for us to consider. All right, now let's go for it. So I need to think about really what the hydrogen ions that I started with and the hydrogen ions that I end up with after I neutralize. Right, so those are the things that I need to kind of consider here. And so, you know, I know that my Erlenmeyer flask of my hydrogen ions that are already there, that this value is never going to change, this calculation we're about to do, because I know that no matter what, I started off with a certain amount of nitric acid here, right? And so I'm going to do some calculations here that I'm going to try to be, you know, quick about this, but I know that moles per liter are equivalent to millimoles per milliliter. And remember that milli just means 1,000, so all I've done really is, you know, I've multiplied by 1,000 top and bottom here. So when I say that I have 0.200 moles per liter, that actually means that I also have 0.200 millimoles per milliliter. And that's just going to make life easier for me because my volumes are all going to be in milliliters. If you're not sure what I'm talking about, that's okay. Stay tuned. All right, so let's take a look at this. So my initial, it looks to me like I have 0.200 millimoles per milliliter, but I only have 50 milliliters of it. So that means, you know, when I do this calculation, I have 10 millimoles of my H+. Okay, so that's never going to change because, you know, I'm not adding any acid and I'm not removing any acid. All I'm doing is I'm just adding base. I'm adding base through my burette. Okay, let's do the same thing for my initial hydrogen ion concentration or hydroxide ion concentration, right? So at this point, I know that I'm starting out with a 0.100 mole per liter, which is equivalent to millimoles per milliliter, remember? But I've only added 10 milliliters. So far, what I have is 1.00 millimole. And that's of hydroxide. Okay, so let's think about this. If I have 10 millimoles of hydrogen ions present, and I have 1 millimole of hydroxide ions, right? Those hydroxide ions are going to be able to neutralize the same amount of hydrogen ions. Let me write that out. So that means that 1.00 millimoles of H+ are neutralized. Okay, so I can figure out my surplus ions by saying, all right, well, I started with 10 millimoles of H plus, but now I've neutralized 1.00 millimoles of H plus using an equivalent amount of sodium hydroxide, and that's going to leave me with 9.0 millimoles of H plus left over. Okay, so those surplus ions are what I'm going to contribute to my pH, right? Because the rest of them, the other 1 mole per millimole was neutralized. Okay, and so now I'm getting there. I'm getting to figuring out the pH because I know that pH is equal to the negative log of my hydrogen ion concentration. So I have the number of millimoles that I have, but I don't have the concentration. So that's the next piece here. Okay, and so you'll remember that we need to calculate the pH based on the concentration of the remaining hydrogen ions, right? And so let's take note of where we are right now. So right now, I know that I have 9.0 millimoles of H plus. And so I want to remind you of an equation we used in grade 11, which was that the concentration of a solution is equal to the number of moles divided by its volume, right? Because I want my units to kind of match. I know that concentration is measured in moles per liter, and here I have moles divided by liters. So that will work out nicely, right? And so in this case, my concentration, the concentration I'm looking for is the concentration of hydrogen ions in solution. And so I have 9.0 millimoles, right? And in what volume of solution? Well, let's think back. Well, in my Erlenmeyer, I started with 50 milliliters of my nitric acid, but then I went ahead and I added another 10 milliliters of sodium hydroxide. So in total, I have a total volume of 60. Right? So I've got the 50 milliliters plus the extra 10 milliliters of base that I added. And so when I work out that calculation, I'm getting 0.15 moles per liter. Okay, now again, remember that millimoles per liter is equal to moles per, millimoles per milliliter is equal to moles per liter. This is why I can just kind of do that. Okay, and so lastly, I just need to do my log calculation. So here we go. I know that my pH is equal to the negative log of my hydrogen ion concentration. So in this case, 0.15. And that's giving me 0.824. So that's the pH that I have of the solution now. So a little higher than before. So let's add that into our table of values so far. So I've got 10 milliliters of sodium hydroxide added, which has changed my pH to 0.824. Okay, all right, so there we go. So I'm ready to do the next step. And so let's just revisit that. So I needed to figure out what the surplus of ions was and use that ion surplus to calculate the concentration of solution, and then use that to figure out my pH. Okay, so carrying on, we know that we're always going to start with those 10 millimoles of hydrogen ion initially, right? That's not going to change. And so if we want to kind of depict that, we've got, you know, our Erlenmeyer flask, and we're going to have those 50 milliliters of nitric acid. But what is changing is the amount of base that I'm adding. So in this point, you know, this is obviously not to scale, but I've added another 50 milliliters of sodium hydroxide to that, right? And that's going to, you know, the 50 milliliters of added stuff is going to give me a total volume of 100 milliliters. And so now I'm going to figure out, well, how many moles of hydroxide do I have in solution? Well, I'm starting off with a solution of 0.100 millimoles per milliliter, and I've added a total of 50 milliliters. So that's going to give me a grand total of 5 millimoles, right? And so that is how many hydroxide that I'm going to have added, which will be able to neutralize 5.00 millimoles of hydrogen ion, right? So, so let's look at my surplus. So my surplus is going to be, well, I start with the 10 millimoles of H plus, and I'm going to have neutralized 5 millimoles of H plus with my base. And so that's going to give me a net overflow or surplus of 5.0 millimoles of H plus. So the solution is definitely still acidic because there's a surplus of hydrogen ions, right? And so I need to remember that that doesn't, I'm not going to use that for my pH. I need to figure out the new concentration, right? And so my new concentration is going to look like this. So my concentration is going to be equal to my number of moles divided by my volume. So the concentration of hydrogen ions is going to be equal to the 5 millimoles divided by my total volume of 50 plus 50 milliliters. Okay, and that's going to give me a hydrogen ion concentration of 0.050 moles per liter. And from there, I can calculate pH. So my pH is equal to the negative log of my hydrogen ion concentration, or 0.050. And that's going to give me a value of 1.3-ish. Let me just double check that. 1.30. So I'm going to take that value and I'm just going to add it to my little table as a table of values. So when I add 50 milliliters of my titrant, I'm ending up with a pH of 1.30. Okay, and so we're going to keep doing this. I'm going to look at phase 4, and phase 4 is where we're going to add we're going to increase the volume of our titrant over to 100 milliliters. Let's see what happens. Okay, so at this point, again, I'm always going to start out with 10 millimoles of hydrogen ion, right, in my Erlenmeyer flask. That's that 50 milliliters. But now I'm going to have reached the point where I've added in another 100 milliliters of my sodium hydroxide. Okay, and so that's going to give me a grand total volume of 150 milliliters of solution. That's going to affect the concentration, right? And so let's take a look at my initial hydroxide ion concentration. So I'm starting out with 0.100 millimoles per milliliter, and I've added 100 milliliters, and that's going to give me 10.0 millimoles of hydroxide. And so those 10 millimoles of hydroxide are going to be able to neutralize 10 millimoles of hydrogen ion, right? Those are going to combine and form water. And so I'm at the point here where I have neutralized all of my acid. I've got 10 millimoles of it, and 10 millimoles can be neutralized. So my surplus, got 10 millimoles minus 10 millimoles is going to give me 0 millimoles of H plus, right? So now how do we calculate pH if we don't have any concentration of H plus? Well, I want to remind you that when we actually neutralize, our hydrogen ion and our hydroxide ion can, produce water. And so we're going to be figuring out the pH of water. Now, your instinct should tell you that our value should be a pH of 7, but let's just kind of, let the math do the talking here. So I know that my pH is equal to the negative log of my hydrogen ion concentration. Okay, but the hydrogen ion concentration in pure water is 1.0 times 10 to the negative 7 moles per liter, or millimoles per milliliter, right? And so that's the value that we're going to put in here. And that's from a previous lesson where we looked at Kw, we looked at the concentration of hydrogen ions in pure water. So 1.0 times 10 to the negative 7 will in fact give us a pH of 7. So I've just taken a moment to include our table of values so far, And I'm going to add that 100. So I've got 100 milliliters of our titrant that's been added, and our pH now is 7. So I'm going to, keep our sig figs consistent here with 2 decimal places. Ooh, that should be 3 decimal places, I suppose. And so there we go. So pH of 7. So as you can imagine, we now have neutralized all of our acids. So any surplus that we see, right, this surplus right here, is going to be hydroxide ions, right? We've kind of neutralized all those hydrogen ions, so the surplus is going to be hydroxide. So I'm going to expect the next pH value that we get in our table to be an alkaline pH value. But let's take a look. Okay, and so as per usual, I'm going to be starting out with 10 millimoles of my analyte. But at this point, I'm saying I've added 150 milliliters of titrant, and so my volume of titrant has changed to 150 milliliters. So I've got 0.100 millimoles per milliliter times the 150 milliliters, and that's going to give me 15 millimoles, right? And so now I'm at the point where I can see that I'm going to have a surplus of hydroxide ions, right? So let's take a look at this. So I'm starting off with 15 millimoles of hydroxide ions, and I'm going to have had 10 of those neutralized by my hydrogen ions. So that's going to leave me with 5 millimole surplus. Okay, so this is where things change a little bit because, I can't calculate pH directly from hydroxide ion concentration, so we've got a little bit of extra work to do, and I'm going to remind you about the relationship between pH and pOH. So I've got my excess millimoles. So what I'm going to do next is I'm going to say, all right, well, I've got my concentration of hydroxide ions is going to be equal to those 5 millimoles divided by, and let's look at the total volume here. Well, I've got my 150 milliliters plus the 50 milliliters of my analyte, that acid. So that's going to give me a total of 200 milliliters of solution, resulting in a hydroxide ion concentration of 0.025 moles per liter. Okay, and so now from there, I can't calculate pH, but I can calculate pOH. Now remember that pOH is equal to the negative log of my hydroxide ion concentration. And so I'm getting a value of 1.60. Now that's, remember that's pOH, that's not pH. And so we need to remember that pH plus pOH is equal to 14. So 14 minus my 1.60 will give me a pH of approximately 12.40 roughly, right? So, so that makes sense. And so that makes sense. Let's take a look at where we are so far. So now, this is my final phase. I've got 150 milliliters of my titrant and analyte, my titrant added in, and that resulted in a pH of 12.40. So we've made quite, these are only 1, 2, 3, 4, 5 data points. This is 100. So that's not a lot of data points to construct a curve, but it does give us an idea about the general shape of the curve. What I did was I took these points, these values that we had. This one seems to be slightly off. And then you can kind of see that, here at a pH of 7 is my equivalence point, right? That's right here. So that's where I would normally sort of expect my curve to go and then up like that, right? And so I'm not really seeing that. That's not what I'm seeing. And so what that tells me is that I needed to have a few more sort of data points in between. And, from here, from this spot right here, this coordinate to here, it looks like I would just kind of connect that sort of like that, right? That's not really what the shape of the graph is. It's typically, represented as. So I need a few more data points in and around that equivalence point to just make my curve look a little bit better. And so that's what I would do. So I would probably pick maybe, well, let's take a look. I would probably pick some values that look like this. So, just a little bit around that equivalence point of 50. That was my equivalence point. And so around that, I would kind of get incrementally smaller and larger data points and go through the same calculations that we just did, but with these different titrant amounts given. And slowly what you'll see is you'll just see more data points kind of fill in that will give you that characteristic sort of titration curve. Okay, so that is the end of the lesson. I hope that helps to at least get you started with titration curves and explains why it is that we're doing the calculations we are. But make sure to reach out if you have any questions.